So this particular course is what we called the phase-space formalism by Wald and collaborators, and also to understand what is called a Wald entropy, black hole entropy. This is fairly mathematical, but the way I have structured the lectures, I will not venture into more details of abstract mathematics, because I will of course tell you where to look at and how to look at. So if you have real interest in knowing the integrities of the details of the construction, you can always go back and look at it. But the main idea of this 5 lectures will be emphasis that, first of all, how we can use this phase-space formalism, covariant phase-space formalism, for deriving what is called the first law of black hole mechanics. And that is the main thing we want to know. And what we will also try to understand that very, very sophisticated as well as a very general idea, what do we mean by black hole entropy, black hole first law? Okay? And you will see that the main advantage of this is that not only for general relativity, any theory of gravity, as long as it has a black hole solution and obeys some technical assumptions, you will see that I'll be able to write down a first law with the entropy, which is different from area. I think this is the first surprise. Okay. If I remember, it is probably the Matt Visser's paper who first noticed that if you have connections to general relativity, area is no longer the Hawking-Bekenstein entropy, but some other local functions defined on the horizon is the plays the role of the analogous Hawking-Bekenstein entropy. But Wald's formalism actually made it clear that given a theory with some Lagrangian, how do you write down that black hole entropy? So that is the main objective of this course. So I hope I'll be able to go in 3 lectures to the expression of the Wald entropy. I will skip certain steps, of course I have to, but we will try to cover it in the tutorials. So today's tutorial, for example, we are going to discuss, Jahanu is going to discuss about the differential form. This is a very basic tutorial, but it is important because some of the notations will be clear. Okay, for example, me and Jahanu is having fight with a minus sign. I hope it will be cleared throughout the day. And next 2 lectures, my plan is to introduce, starting from the Wald entropy, is something called a physical process law, which is in some sense a more physical and simpler way in look at the first law for black holes. And I will derive physical process law for any general theory of gravity. I will look at, tells you what are the assumptions, what are the problems, and so far what is the extension. And then I will talk about, at the end, a little bit about classical second law and maybe semi-classical second law, if the time permits. But the main emphasis will be to tell you, at least I may not be able to derive everything, but teach you that what is the state of art, what has been achieved in proving and extending these laws to an arbitrary diffeomorphism invariant theory of gravity, so that you can start from there, okay, if you're interested in these topics. That's the main idea of this course. So the second lecture onwards will be mostly on black holes, but the first lecture will be very basic classical mechanics. That's what we are looking at. So, of course, all of you have learned classical mechanics in a much more greater detail. So so if you start with classical mechanics, or at least the analytical way of mechanics, I hope this font size is okay for everybody. Is it visible? Okay, good. And the main idea of classical mechanics would be that I give you a Lagrangian, okay, and you construct the equation of motion out of it. So the Lagrangian, so I give you first a set of generalized coordinates, sorry, Q, okay. Given the set of generalized coordinates, what is the generalized coordinate? Of course, you remember that I have coordinates and then what do the constraints? The system may have constraints. I will assume simple holonomic constraint, but you can do this construction for non-holonomic constraints also. Then I have this set of generalized coordinates. Okay. And given this set of generalized coordinates, I'll be able to construct what is called a Lagrangian. So Lagrangian depends on Q dot, and possibly time. Most of the time, we will ignore this time dependence. Okay? We'll only work on Q and Q dot, because that is what is relevant to our discussion. Note that this is the way we'll define the Lagrangian in classical mechanics. So in your elementary courses, you have been told that Lagrangian is kinetic energy, but minus potential energy. But slowly, I am sure that you have realized Lagrangian is the starting point. Okay. So a theory is defined by giving the Lagrangian. It's not like that you obtain the Lagrangian for more fundamental objects. Okay. This is what the starting point. My theory differs from your theory if my Lagrangian differs from your Lagrangian. Okay. And that's the beginning. So this is your input. So this is the idea in point particle mechanics. Of course, if you are in a relativistic theory, what you do is that if your fundamental constituents are some field, it would be scalar field, vector field, fermions, okay, some representation of the Lorentz group, because you are looking at relativistic theory where SO13 is the invariance group. In that case, you'd like down your Lagrangian constructed out of phi, your field. I am not considering the indices on phi. It could have its own indices, both internal and external indices, and then of course, you ensure that this guy is a Lorentz scalar. A familiar example is your del mu phi Lagrangian in the scalar field. Okay, and you can construct Lagrangian whatever you want. Generally, in physics, we keep ourselves limited up to q dot. Okay, of course, you could ask that why in physics. I could have asked a q double dot Lagrangian which depends on q double dot. Then I will have higher order differential equation as my theory of equation of motion. Of course, in nature we don't see that, and there is a deep theoretical reason for it, because if you have these higher derivatives, the equations resulted will have some kind of instability, something called Ostrogarsky's instability. Although there are suggestions in the literature how to bypass those instabilities, but more or less we will only confine to Lagrangian, which depends up to q dot. Will not go to higher derivative Lagrangian, though they are a subject of their own interest. Okay, and there are very, very interesting recent extension of those things. But so the Lagrangian description works in something called configuration space. And I will denote configuration space by C. Okay. And what is the configuration space? It's quite easy that if I have the generalized coordinates, if there are small n number of generalized coordinates, I can construct a space where each point is a generalized coordinate set. So therefore, this is the configuration space, which is the n-dimensional space of the generalized coordinate. So the configuration space is, for example, if I have a single point, I require no constraint. I only require x, y, z. So then configuration space is a 3 dimensions. Generally, we will assume some smooth structure of the configuration space is assumed to be manifold. Okay, but those details may not bother us at this stage. So configuration space is n-dimensional space of generalized coordinate. And an example of configuration space would be, for example, if I have a point particle, let's say if I have a point particle, it is easy to understand that configuration space is simply R. Now, suppose you have some constraint and you say that the point particle is constrained to move on a sphere in R3. Okay. Then what will be the configuration space? Particle on a sphere, and that will be S2, right? So you can use angular coordinate to specify the configuration space of the system. Suppose I have a rigid body. Can you tell me what would be the configuration space? Any idea? Anybody? So I have a rigid body. How many coordinates I'll require to fix the, anybody? 1, 2, 3, 4, 6. So I need to know where the center of mass is, and I need to know Euler orientations of that. Okay. So configuration space is a 6-dimensional space. So similarly, for various given, if I give you the dynamical system, you will be able to write down the configuration space by looking at the generalized coordinate. Okay, that's very easy. Good. Whereas, so the Lagrangian mechanics takes place in configuration space. The paths by which we extremize the action lives in configuration space. Remember, in the configuration space, I only specify the Q. I do not specify the Q dot. Okay. So as a result, given a Q, there could be different Q dots. So therefore, you can go into different directions. As a result, the path in configuration space can intersect. Because from a single point, your Q is same, but Q dot are different. So can you go into different directions? Okay. So that's important to understand. With the configuration space, we know that Lagrangian, I can go into the Hamiltonian picture. I can go into the Hamiltonian picture. Hamiltonian. In the Hamiltonian picture, I will define it more rigorously, but we work in colloquial term what we call a phase space. Right? We work in what is called a phase space. I'll define in more general, how do I define a phase space? This is the whole idea that given a theory, suppose it has, let's say, gauge redundancies, it is highly non-trivial to understand what is the actual physical phase space. That is the main idea of the construction behind the covariant phase space approach. But very simply in classical mechanics, what we will do, that phase space is basically the space of the generalized coordinate as well as the canonical momenta. And in more colloquial term, we know that we denote this is 2n dimensional. It is event dimensional. This is important. Okay. So phase space is 2n dimensional, okay, given the n with the degrees of freedom of the system. Very good. And I can define, for example, in this abstract 2n dimensional space, I can define a function on this phase space function. And those functions could be a function in Q and P. I'm omitting indices. I will be careful of indices later, but at this time, we need not put indices. Okay. And then I know that, of course, I choose functions which does not explicitly depend on time. You can put explicit dependence on time. The construction will go ahead with some extra term, derivative terms, partial derivative term. In that case, so a good example of this function is angular momentum, energy. All these are functions in space time. Both Q and P are the simplest function you can think of in phase space. And in that case, we have this time evolution equation, df dt equal to classical Poisson bracket f comma. Okay. This is the fundamental equation in classical mechanics, which tells you how the phase space quantities evolve through the Hamiltonian. Okay. If it is explicitly dependent on time, there will be a del H del T term out this side. Okay. Otherwise, it's the same equation. You can always work it out. And so these are in elementary classical mechanics. You must have derived all those things and you know how to derive it. So I'm not going to give you the derivations of any of this sort. Okay. So note that how do we define what is a Hamiltonian? Okay. So in classical mechanical picture, the Hamiltonian is the generator of time translation. Okay. So Hamiltonian, I can think of Hamiltonian is the generator of time translation. Now in point particle mechanics, even in ordinary field theory, it's not of a big problem once you define this, but you have to be very, very careful. Once you define, let's say, try to find the Hamiltonian of a covariant theory or a theory which has gauge redundancies. Because suppose you're looking at a theory which is diffeomorphism invariant. You have to be very, very careful. What do you mean by time? Because I have to be ensured that your time and my time, which is related by a diffeomorphism, should give me the same physics. So therefore, what do you mean by the generator of time translation has to be carefully defined. Okay, and that leads to a lot of important consequences, at least for gravity. Second, another very, very important thing is that you have to specify what is the time. Okay, so that means in a covariant theory, you have to tell me what is a 1+3 split of spacetime. Now, there are a lot of technical assumption goes in once I say that this is allowed. First of all, why it is allowed that any arbitrary spacetime, I should be able to do a 1+3 split consistent. And in general relativity, there are solutions where you may not be able to do it. For example, if you have closed time-like curve. Okay, suppose you have a time machine. Okay, I hope you don't. Okay, suppose you have. Okay, that is one of the reasons why time machine should be banned, because you may not be able to do Hamiltonian formalism correctly. Okay, I mean, that's a good way that we should not have time machines. Okay, even if we can build it, we can ban it. Okay, Hamiltonian formalism will be difficult. Okay? So there is a technical terms which is used. I'm not going to define it, but if you're interested, go and look at GR literature. It's called globally hyperbolic. Okay? It is important the spacetime to have globally hyperbolic character. In some sense, it means that there exists a Cauchy surface. Okay, I have a, let's say in Minkowski space, I have a notion of T equal to constant surfaces extending from infinity to the origin. Okay, and if I give fields on this, I'll be able to give the time evolve this field according to some box phi equal to 0 equation, and gives you the solutions in subsequent time at all subsequent points. So given the initial data, the solutions can be predicted at any subsequent time. Okay, such a spacetime is called, such a surface, if it exists, we call it Cauchy surface, and it's equivalent in saying that the spacetime is globally hyperbolic. Okay. It is important of this idea. So I'll be throwing at you mathematical jargon, which I will not define it, because if I want to go define it, it will take half the course, okay, which I don't want to do. But I urge you that look at the literature, and the way to understand this object is, I'll give you the technique, globally hyperbolic. If you really want to understand this subject, this topics, is always better to look at counter examples. Okay, look at spacetimes which are not globally hyperbolic. That will give, instead of the definition of globally hyperbolic, that counter examples will help you to understand what is going on. Okay. So therefore, Hamiltonian formalism, unlike the Lagrangian, is inherently not covariant, because it gives you, you have to specify a 1+3 split. And that is a lot of problem. For example, in gravity, the Hamiltonian formalism, you have to be very careful in performing. You have to understand how do you implement that idea of covariance within the Hamiltonian formalism. Okay. So in some sense, the covariant phase space formalism is the idea that how do you restore covariance in Hamiltonian. Now, you may say that, why would I want to do that? Is it important? Well, it is extremely important. For example, Hamiltonian gives you the notion of conserved quantities. Okay. In gravity, if you want to define, so in gravity, there is no local definition of energy momentum tensor. Okay, there is no local energy momentum tensor for gravitational field. Unlike electromagnetic field, where I have energy momentum tensor for the electromagnetic field, whose energy is like E square plus B square, which all of you have learned in your BSCs. That is not true for gravity. I cannot define a covariant object whose integration over a Cauchy surface or T equal to constant surface give me the energy. That is not possible in gravity. And that is main reason for that is actually equivalence principle. You can always go to a local frame where gravity vanishes. So you have to have a covariant way. You have a question? Sorry. No. You have to have a covariant way of defining what is called the energy of space-time. And for gravity, such definition requires a construction of the Hamiltonian. And that is what is called the ADM construction, which is done in famous ADM paper and later extended by many people. Okay. ADM formalism, the standard ADM formalism works as long as the space-time is asymptotically flat. Of course, otherwise, if you have asymptotically de Sitter space-time, you have to be very careful in constructing these conserved charges. So therefore, you need a form, a covariant way of doing Hamiltonian formalism to define these conserved charges. Because if you do not define, forget about theory. even defining observational quantities, you may end up in trouble. For example, if I ask you how much energy the gravitational wave had carried out from the system, to define this object in a gauge invariant way is tricky. Okay, and therefore this is one of the motivations for doing this, to define consequence. Of course, as Wald has understood, this way of doing things will end up give you the first law in a very, very unified way and identify the Noether charge of killing isometry as something to do with the black hole entropy, which we'll discuss. Another main motivation is that we know how to quantize things in Hamiltonian formalism, easier than path integral formalism sometimes. Okay, so if you want to create a Schrodinger equation for quantum gravity, okay, H psi equal to E psi. Okay, of course, there is not easy to define such equation. You require the Hamiltonian forms where all the constraints have been taken care of. You want to understand the phase space where all the constraints are satisfied, the physical space, phase space. And therefore, it is important to understand this mathematical structure. So these are main motivation, and one of the main motivations is it's interesting to do this calculation. Okay, that's obvious, always there. So with this motivation, so what is the ultimate aim is construction of phase space of a covariant theory. Unfortunately, I'm not going to give you the formalism, okay, because it's too long. What I'm going to do is that I will indicate, at least in the lectures, what are the ways to do it and what are the right reference to look at it. And also, what is the consequence once, if I could have done the full formalism. But first, let's go ahead, okay, how far we can go. So with this introduction, let us introduce a simple notations. Okay, so as I told you, yeah, please. Yeah, okay. Are you talking about in ordinary quantum field theory, one like electrodynamics? In that case, you can always equate, and we know the dictionary how to go from Lorentzian picture to Euclidean picture, the I epsilon prescriptions and the corresponding Euclidean picture. Okay? That is fine, but in gravity, equalization is non-trivial rather. First of all, that is one of the reasons is that path integral of gravity is ill-behaved because of the presence of conformal tensor terms. Okay, so weak rotation in gravity is a serious issue. Even in classical gravity, for example, if you have a curved black hole, finding out the Euclidean version of curved black hole is tricky because if you do T to IT, you will end up having complex matrices. So Euclidization for gravitational physics is rather non-trivial, that would I would say. But sometimes it gives you very, very interesting result. For example, if you are doing it for, let's say, Rindler spacetime, that is one of the tricks to get into the black hole temperature, this KMS states or something like that. So in certain cases, it is possible to define the Euclidization, but otherwise it's a tricky thing, or at least for gravitational physics. But field theory, we know how to do Euclidization. At least, okay. I mean, I epsilon prescription itself has its own interesting properties. Okay. There's a very interesting review, I think, core paper by Witten on this I epsilon prescription on path integral. Maybe you can look at it. Okay. So we'll introduce notation. So remember that I told you that phase space is a 2n-dimensional space, and therefore vector in the phase space. See, I'm assuming, look, I'm not justifying these terms. I'm assuming that I would be able to construct and introduce notions like vectors in phase space. Okay? These are given to me. Okay. And you require a certain amount of structure in phase space, which we'll probably discuss. Maybe today Raji will discuss in the symplectic forms but for the time being, allow me to do it. Okay. So I will define what is called a symplectic notation. The idea is that a vector in phase space will have 2n-dimensional component. It's very simple because it is 2n-dimensional space, it will have 2n-dimensional component. So let me use that fact and construct an object which will Qn, P1, P2, P. Okay. So this object is a 2n dimensional object. Its first n components are Q, the generalized coordinate, and last n components are by generalized momentum. Okay. Very good. Okay. Now you should be able to show that your Hamiltonian equation, and this is standard stuff in Goldstein, you should be able to write down in this notation, eta dot equal to J del H, del eta, where this J is a matrix and J is given by this way, 0, 1, minus 1, 0, which is a 2n cross 2n matrix. That means each of this is the identity matrix n cross n. This is the identity matrix with a minus sign n cross n. This is n cross n 0, 0, 0, 0 matrix. And this is similar to that. So total, this is a 2n cross 2n matrix. This is almost trivial. You put this matrix, you will have 2n number of equations. You should be able to show that this is nothing but completely equivalent to, okay, of Hamiltonian equations, which is Q dot equal to del H del P, and P dot equal to minus del H. You should be able to show, and that minus sign is there. Okay. So please go ahead. These are trivial, almost trivial construction, but it's good to. You can also show that using this eta and j, you can define what is called the Poisson bracket between two functions in space. U and v is again just like f. I construct them as two functions in space. Let's say angular momentum, two components of angular momentum. Okay. You should be able to show that this is nothing but del u del eta transpose j del v del. Okay. Again, so these are equations which you may require. Please do try to derive this. These are standard equations in Goldstein also, I'm sure, discusses. Okay. So the main idea is that the solution of these equations will tell you how the system evolves in the phase space. Just like the Euler-Lagrangian equation tells you how the trajectory evolves in configuration space, here the phase space trajectories are determined by the solution of Hamiltonian equations. Remember, unlike Lagrangian equations, Euler-Lagrangian equations, Hamiltonian equations are 2n dimensional first order differential equation. Okay, that's important. They are 2n dimensional first order differential equation. Now, so let me write it. Time evolution of the system is trajectory in phase space. Now in configuration space, trajectories can cross. Can the trajectories cross in phase space? The opposition that they can or they cannot. They cannot, right? Trajectories in phase space cannot. And that is simply because in phase space you give both the position and the momentum. It's a two, your initial conditions are also 2n. N momenta and n positions you give, and you solve first order differential equation, and then assuming certain good properties of the initial data, the solution is uniquely determined. So therefore, you cannot have trajectories crossing and going in different directions. This will violate the uniqueness of the first order differential systems in mathematics. So therefore, the trajectories in phase space will never cross. They can go up onto each other, okay? Just like the ellipse in phase space of the harmonic oscillator. Okay. So with all this construction, let us go ahead and be a little bit adventurous and write down a few more mathematics. Okay. So what this construction says that the configuration space is main fundamental object for Lagrangian mechanics, and in the configuration space C, we consider it to be n-dimensional manifold. That means there are smooth properties, I will assume, and there is a local chart exist. Okay, locally these manifolds will be heat. Okay. So I should be able to use those properties, differential structures on this manifold. Okay, that's the whole idea. Assuming that the configuration space is a manifold. So what it means is that if I have a Q point on this manifold, belongs to this manifold N, then what does it not is? It's nothing but N real number. N real numbers. These are basically coordinates. Okay, where I goes from 1 to small n. Okay. Good. Now, given a manifold, I can define the tangent space of the manifold. And the tangent space is denoted by Q, TQM. What it means is the tangent space of the manifold done at the point Q. I can do at an arbitrary point. I can look at the what is the tangent space of tangents, all tangents at that point. Of course, if I have an n-dimensional manifold, you should be able to convince yourself that the tangent space is also has dimensionality n. And if you are not convinced, look at the Wald's book. I think in the chapter 3 or chapter 4, he proves this construction that given an n-dimensional manifold, you should be always find an n-dimensional basis on the tangent space. Okay. And therefore, the tangent space has the same dimensionality as that of the manifold. It may sound almost trivial to you, but I urge you to look at the Wald's proof. Okay. That how do you ensure that the tangent space has same dimensionality as that of the manifold itself? Okay. And then what will be the basis of the tangent space is very clear. A good basis of the tangent space is basically this, basis vectors will be del del Q. Now I am being very careful, put appendix. Okay. What I mean to say, this derivative operators along the directions of Q's forms a very good basis. These are coordinate bases, and usual notation, I will sometimes notate them as del I. Okay. You should be able to convince yourself that if Qi is transformed like a covariant vector, this object transformed like a covector. Okay. Good. So they forms a very good basis in the tangent space. That means if I have a vector in the tangent space, any vector in the tangent space, vector, I call it V, and that is nothing but I can think of this vector as the linear combination of components with the directional velocity, like Vx I cap plus Vj, whatever you do. And then I can call it Vi del R. This is exactly what you do in Cartesian coordinate system also. This is just a fancy way of writing things in Cartesian coordinate system. Think of what do you mean by x-axis in Cartesian coordinate system. This is the direction where x increases or x changes, okay? So del del x, del del y, del del z, these are three axes. Okay. You happens to call in a coordinate basis the component of that vector to be 1, 0, 0, xyz basis, right? It's the same thing, but written in a funny notation. Okay. Is that clear? So this is what the vector is with the tangent vector. In any vector in the tangent space, I will be able to write down in the basis in the tangent space. Very good. So I can construct, so this is for any number of, so think of this is a manifold. I construct the tangent space here, okay, at this point P, and any vector, this vector, my drawing, it's not very clear, but this vector lies on the tangent space, okay, I will be able to write down it into this basis. What is important to understand that if I know the trajectory of the particle in the manifold, okay, so each point I can construct the tangent space on the trajectory. Then I have a very special vector, which is the tangent vector to the trajectory itself. Okay, as I told you, the time evolution of the system means it has trajectory in the phase space. I can think of a vector which is tangent, which is always tangent to the trajectory, and therefore also a member of the tangent space at each point of the trajectory. If you think a little bit carefully, this is nothing but the velocity vector. So a funny way of calling, okay, if V is the tangent to to the trajectory, then we call it, V is called velocity. And then notation wise, what I say is that Vi is my Qi dot. Okay. Good. So therefore, what do I have for each point in the phase space or also in the configuration space? Let's first consider the configuration space. I have Qs and Q dots or VIs. Okay. Each point, I have the point and the tangent vector of the trajectory, which is a member of the vector space at the tangent space. Tangent space is a vector space, which again has n-dimensional basis. Once I this structure, so what I can do is that I think I can go at the end, or is there a limit in this direction? Is it a semi-infinite line, or? Let me try. Okay, let's see. Ajith, maybe I'll stop. So then there's a Dirichlet boundary condition in both sides. Okay, good. Okay, let's go ahead. Okay. So I have this structure, Qis, okay, and I have this Vi's. Okay. So these are points and the tangent vector, this points. Okay. So yeah. Yes, you need a parameterize that up. I am assuming that your parameter is by that lambda. Using that parameter also, you can convert it to some del lambda A. That's the, but I will not require it at least for this. Here, the parameterization itself, very simple parameterization is the time itself. But I will not go into that, at least here. Okay. So that is why I kept unspecified. What do I mean by dot? Good. So what does this collection gives? This collection gives me set of points on the manifold and the vectors in the tangent space. Okay. So let me write these collections. They gives collectively, what do they define? Product of the manifold, a product, Cartesian collection, Cartesian product, sorry, of manifold, along with the, and the tangent space. By product, I don't mean A into B. I mean the Cartesian product. So the collection of sets. Okay, A, B. A, so take the element from A as well as take the element from B. This is a Cartesian collection of sets. So beautifully, you can define a structure with this. So mathematicians, of course, have given it a funny name, that what is called a tangent bundle. The name itself suggests what it is, the bundle of tangent spaces. Okay, I mean, so many tangent spaces, collection of tangent spaces, bundle. And the way we will define is that you take the union of all such Qs, okay, and tangent spaces on this, along with the manifold itself. Okay. And this set, you call it tangent bundle. So each point, you have the points. That means you're looking at all the points on the manifold. And at each point, you are looking at the tangent space. And that is what construct is called a tangent bundle. And we will call it TM. Okay. Sometimes M is called the base, okay? And there's a fiber exists, but let me not go into those mathematical definitions. Otherwise, see, I'm deliberately not going into definition lemma code, because this is probably your first course on these structures. It is okay to understand in an intuitive basis, but later you can always go into more rigorous mathematical literature where you will know how to define this structure in a more mathematically rigorous way. Good. Now you see mathematically, let's go to the first part of the board. I define this Lagrangian, which is a scalar in a theory, so that the equation of it's independent of the coordinate choices. So what is happening is that it takes values. If you ignore this time, it takes value from Q, from the manifold, and from Q dot, which is the element of the tangent space, and gives you a scalar number. Okay? So a formal way of defining my Lagrangian would be Lagrangian L is a map, okay, which takes elements of Tm, goes to R. It gives you a number. Is it a linear map? Depending on what kind of Lagrangian you are choosing, right? If you have objects which are higher derivative Lagrangian, it need not be, okay? So you take an element, so you take Tm means you take Q and V, put it into the Lagrangian's definition, what you get is a number, a scalar. So therefore, it's a map from Tm to Q. Okay, so that's a, yeah, please. Okay, so I have ignored the time. You're absolutely right. If there is a time, then you should consider, so suppose the Lagrangian depends on Q, Q dot and T itself. So then the Lagrangian lives on Tm cross R. Another R is real line, and that real line is related to that time. But for most of our construction, the time will not play much a role. So I'm ignoring, I'm calling it. Yeah. Mm. 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 No, I think it's direct. I think I have to look at it. If I remove. Yeah, I also think so locally, but globally it depends on what kind of fiber you are talking about. But maybe I can discuss it later. Good. Good. And then with this Lagrangian, of course, you can construct the action and then we can look at it. Okay. So this is one way we can think of mathematically what do we mean by Lagrangian as a function from tangent bundle to R. Map from tangent bundle to R. So to understand, how do we understand the Hamiltonian from this language? Okay. So we have our Hamiltonian. The first construction of Hamiltonian is that you have to find out the canonical momenta, right? If I want to pass on from Lagrangian to Hamiltonian, you first construct the canonical momenta, okay? So your first construction is that I give you a set Qi, and then how do I write it? Q dot I, Qi, Q dot I. You get Qi and canonical momenta. Note, I'm writing it downstairs, okay? And why I'm doing that? Because the definition of canonical momenta is del L, del Qi, Qi. Okay. So therefore, unlike the Q apis, which transform like vectors, this guy will transform like a covector. Okay? It's clear because you're taking derivative with respect to up in this. This is definition. This is a starting definition. Okay. This is motivated by the fact that from the particle mechanics, that this Hamiltonian plays the role of the energy and generator of time translation. So therefore, we start. This is the starting point. Okay. There is one very important question you have asked, that I should be able to invert this equation to express Q dot as a function of P. Because note, your Hamiltonian is P Q dot minus L. But if you keep Q dot in the Hamiltonian, your examiner will cut marks. Like remember in BSc this, okay, your marks has been cut because. So this equation allows you to invert Q dot in terms of P, right? A very simple but highly instructive is, if I have half m Q dot square, okay, I know that P equal to del M del Q dot is M Q dot. Then you do an extremely non-trivial step. You write Q dot equal to P by M. Okay. You may think this is trivial, but note that what you are doing is that you are expressing Q dot as a function of P. So in your Hamiltonian, you can replace Q dot as P. But that may not be always guaranteed. For example, if I have a matrix here, okay, suppose I define Pj equal to Aij Q dot J. Whether you will be able to invert it or not depends on whether the matrix is degenerate or not. The determinant of the matrix is 0 or not. And there are Lagrangians known as singular Lagrangian for which this inversion is non-trivial. Okay. And the singular Lagrangians are sometimes called, sometimes represent the presence of constraints. And most of the 20th century physics is to understand how to quantize singular Lagrangian. Okay. And these are, for example, even in QED, you will have this problem because the Lagrangian is independent. There is a constraint of H0, the zeroth component of the mu. Right? The momentum corresponding to A0 is ill-defined. And therefore, one has to be careful in constructing the full time evolution. Okay. So therefore, you can always do that, but singular Lagrangians requires extra prescription. Depending on the nature of constraint, the prescriptions will vary. For example, if it is a second constraint, you can use, I'm not going to define what are those, you can use something called Lagrange multiplier and go to a subspace. If it's a first class constraint, it's non-trivial. Good. This is related to the convexity because this is related to the second derivative of the Lagrangian, convexity of, yes, exactly. You can't go to heaven. This is exactly that's very good way of saying that for convex properties, you can do the Legendre transformation. You can draw this tangent, okay. Okay, this is classical mechanics 101. If you want to know, there is a very interesting American Journal of Physics paper. Look at it. The physical meaning of Legendre transformations. There it is. Say, I mean, I'll try to download it and give it to you. Okay, good. But the main fact is that this guy behaves like a covector. Okay. If I start with, okay. And therefore, the covectors, of course, do not live in the same space of the vectors. Okay. So just like I have invented a name that vectors lives in the tangent space, here let me also invent a name that this guy lives in what I call covector from vector, tangent to cotangent. Okay. So there's a continuity of names. I call it, this guy lives or member of what I call cotangent space. Cotangent space. So let me try to define what is this object. So I'll go to the, no, this is not Dirichlet. This is periodic boundary condition. We're going there. Okay. Good. Okay. So, okay. So, how do I define what do you mean by a covector? Let's start with it. Okay. So suppose I have, let's do it in a very simple rectangular coordinate system, Cartesian coordinate system. Okay. Suppose I have a function f, which is a function of x, y, z. Okay. Okay. I can construct what is called a differential f, which is nothing but del f, del x, dx plus so on and so forth. Del f, del s, dy, del f, del s. Okay. Good. That's everybody, all of us knows. Okay. Now, what is quite interesting is that what you can do, you may say that suppose I have a vector v, okay, which is from the tangent space of the manifold. Given this df, you can construct a rule of scalar product akin to the ordinary scalar product, where you say the rule is this, that this df acts as a linearly on this vector v and give me a scalar number. Okay. And that scalar number for this case, it's very clear that you will write it as, what should I do? You should write it as some Vi, let's say, del F, del X. I. And that belongs to R. So given the differential df, I can construct this object, okay, such that there is a scalar product rule between df and, so there is a map, so df takes a vector and gives you a number. And sometimes we call this object df as a one form. So today there is a, in the tutorial, Jahanur will formally introduce what is called a form, okay, using more formal traditional way. But intuitively you can think of a form is something, a one form is something which eats a vector and gives you a scalar. It's a linear map which takes the vector as input and gives you the number as output. That's the one very intuitive way of defining what is called a one form. Okay. And this one forms is, look at now the structure Q, P. In ordinary physics, ordinary pre-sophisticated physics, we used to call vectors covariant vector and contravariant vector, or covectors and vectors. Okay. So instead of that language, we will call Pi to be a one form, okay, which lives in the cotangent space. So therefore, in this language, we will form, so this lives or member of cotangent space. Cotangent space. And we will invent a notation for this, E star Q. Okay. Just like we call the tangent space to be TQ. Good. Let's go ahead with this construction. So, in more formal way of saying, a one form is an object which maps vectors to R. Or in other words, it's a linear map from TQM okay, good, very good. So given this one form, of course, the next question is, can I construct two form? Can I construct three form? Can I construct P form? What are those objects? Okay. This is like saying, if I have a scalar, by taking directional derivatives, I can construct vectors. Given two vectors, I can construct a map which takes two vectors, gives you a scalar, and define tensors as a multilinear maps. Okay. I am doing the analogous construction, but on the cotangent space. From one zero form is a function, one form is a differential of that function, and then we are going ahead more with two form, three form, and four form, and more. To do this construction, it is important for us to first understand a basis for one form. Basis for one form. And that is easy to understand, that it is clear. Look at this. You may think of these are the components of the one form if you take dx, dy, dz as the basis. Okay. So therefore, a good basis for one form is this differentials dxi's. Okay. And if I have any one form, call it suggestively P, okay, I should be able to write down P as Pi dxi in that basis. Okay. So dxi's forms a good basis for one form. Good. Yeah. What do you mean this way? Yeah. Yes, yes. Maybe, okay. Let's keep it this definition for the time being, okay, because this is what I'm going to use this notation. It is exactly dual, huh? You're right. Okay. Yeah. So yeah. So you flip it, then it will be clear. Okay. But we can keep this notation. There will be absolutely no problem. Good. Where are we? Oh. What is the time now? 15 minutes more. Yeah. Okay. Good. Let's go ahead. So if this has the basis, so I want to construct basis for two forms. Okay. So first I have to define what do I mean by two form, and then construct a good basis. Okay. For these two forms. Okay. So before we do that, okay. So let's call omega to be a two form. So what does omega will do? It will take two vectors, let's say u and v. So let's say u and v are vectors. So one form takes one vector and map it to a scalar. Two form will take two vectors and map it to a scalar, but in a bilinear way. Okay, you have to be careful. Okay, so therefore, that object I will call it u and v. Okay, so it takes its arguments are two open slots. It takes u and v and gives you a scalar. That's the idea for a two form. Okay, so let's construct two forms using two one forms. Okay, let's see how do you do that. So I give you forms A and B. These are one forms. That means what do I mean by one form? I know what is the action of this one form on vectors in tangent space. Okay, so therefore it means I understand what are those objects. B. Okay, as a linear map from vectors to real. This is given to you. Once I said these are one forms. Okay, good. Now let us now construct u and v. So let's say this object is defined by this relationship, which is AU BV minus, AV B. Okay. I'm doing everything in the component language. Okay. I will make it abstract later, but let's understand this. Okay. You can clearly see that this is a rule which is antisymmetric. It's a bilinear, and it takes you vectors and splits out a scalar. Okay. Sometimes we will write this rule as A cross B minus B cross A. What does this mean? These are nothing but outer product. Okay. I'm just multiplying components. Okay. So these are sometimes called outer product. I emphasize, please come to today's, we have already uploaded the tutorial. Look at the definitions and the construction of the forms we have given. And maybe we can do few Cartesian forms. I think that will be easier to understand what is going on. Okay. Let's go ahead. Okay. So if we want to define this object as a two form, starting from the one form, let's see what is the basis of this object. So I told you A and B are one form. So therefore, I should be able to write A equal to AI dxi, B equal to BI dxi. That is because these are one form and dxi is a good basis in the space of one forms. Okay. Okay, good. What about V's, U's and V's? These are vectors, lives in tangent space. And the basis here is UI del I and VI del I. Okay, because directional derivatives forms a good basis in the tangent space. Is that notation clear to everybody? So I'll explicitly give you the coordinate basis components of the one form as well as the vectors. Okay, good. If I have this, let us now understand what is this object then. This object. So then what is omega uv? How does omega acts on these vectors? It's clear that I'll just put everything here, and you will see this is nothing but AI Bj minus Aj Bi Ui. Is that clear? I just substituted it here. Okay. This is AI Bj, Aj Bi, and Vi Vj goes common. Clear? I call this object to be omega Ij. Ui. This is completely antisymmetric. Okay? Clear? Okay? Is that part clear, everybody? Now, what I will do is that I will define what I call wedge product. Wedge product. Formally, a wedge product is basically construction of higher forms. Given a one form, how do you construct a two form? Given a two form, how do you construct a three form? So let's first write down symbolically what do you mean by wedge product. So the wedge product would be, the notation is dxi wedge dxj is completely antisymmetric. So therefore, minus dx j. Let me first write down the definition. I think that will be easier. So it is dxi dxj. By the way, this I am doing for coordinate basis vectors. Okay. I mean, basis of the one form. You can in principle define this for any one form. But let's first do it for here. Minus dxj. Completely antisymmetric. In terms of outer product, I'll define this object. Okay. Now my claim. Claim is omega uv. I should be able to write down this nothing as this object. Okay. dxi wedge dxj acting on uv. Okay. This is the claim. Okay. That this omega, how does it acts on u and v, is nothing but how omega ij dxi wedge dxj acts on u and v. Okay. Let's understand whether this m is correct or not. And that is easy to understand. This is nothing but 1 by 2 factorial. This I write it as omega ij, and you clearly see if I put this definition here, look at how it acts on u and v. It is clear this is nothing but ui vj minus uj vi. And therefore, this helps me because this is antisymmetric. This is antisymmetric. I can get rid of this 2 factorial and I call it omega ij ui vj, which is exactly how this acts. Okay. So therefore, I can use this wedge product to write down. So now if you forget this object and this object, I can represent omega by using, so of course, repeated index means there is a sum, of course. So I would be able to represent a 2 form as the sum over this antisymmetrized wedge products. So therefore, I will say a 2 form is an object which is a bilinear map from the space of tangent space to the R, and it will be written as omega to 1 by 2 factorial. Omega ij, this is in some sense the component of that object, dxi wedge. Of course, there is a sum over all possible i's and j's. Okay. So you clearly see, now compare with the one form, P, which is pi dxi. And this is for 2 forms. You clearly see the basis of one form where the space spanned by dxi's. The basis of 2 forms, that space is spanned by dxi wedge dxj. Okay. So I will say that dxi wedge dxj is a basis in the space of two forms. Okay. Similarly, if you have R form, how do you write down an R form? That is easy. An R form, call it omega R, will be 1 by R factorial. Omega, call it mu1, mu2, dot, 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 mu R, dx mu1, wedge, dx mu2, wedge, dot, 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 wedge, dx mu1. So therefore, this R factorial is there, exactly the reason why we have this 2 factorial. So that if I go to coordinate basis, completely antisymmetric structures get away this factorial. And therefore, this becomes a basis in the space of R forms. Okay. That's very nice construction. And we can go ahead and we will use it extensively when we will talk about, let's say, Wald's formalism. By the way, suppose I have n dimensional manifold and I have n plus 1 forms. Like, what is the top form I can go? N, right? And 0 form is a function. 1 form is dual to a vector, what we call covectors. Okay. In chooser, why? I mean, from this R form, yeah. The space of R form, where, because these are wedge product, completely antisymmetric, therefore the dimensionality of this space here. Yeah. Okay. Clear? Should I go ahead? So with this construction, I have 10 minutes or 9 minutes. Okay. So let's little bit understand this one form PI, which we obtained from the classical mechanics. Okay. So you may ask how P acts on vectors, or let's say velocity vectors. Velocity vectors. So the velocity vectors are vectors in the tangent space. P is a one form. So this question is completely well defined. That how P, which is a one form, is a linear functional acting on the space of tangent vectors. So this is a very well defined question. And you can write down the answer. So symbolically, I call it PQ dot. Okay. P is the one form and Q is the member of the tangent space. Okay. And therefore, this is nothing but Pi dxi in my basis, because one form has this basis, and this object is Qj dot del del Qj. Why this? Because this is a vector, velocity is a vector in the tangent space, and this is the basis in the tangent space, and this is component. Now you clearly see this is nothing but Pi Qi dot, and this gives you the delta ij. Okay. Yeah. And this is usual way we would have expected that this has to happen. Okay. Now, with this, we can also introduce another vector. We call it x or chi, I don't know, depending on how curved this line is. Call it capital X or chi. Okay. So this vector, I will write it like this: xi q del del q plus x p I del del p I. Be careful that, no, sorry. Note that I've been a little careful in putting indices ups and down carefully, okay? Because I know which one is a one form and which one is a vector, okay? Now look what is happening. What is this object? Obviously, it has 2n dimensions, 2n components. So this is a vector in the phase space. Okay. And not only that, look, what is happening is that this guy has a component along q direction this and p direction this. Okay. Good. So with this notation, let us introduce a very simple one form, which we call theta, whose definition will say Ti TQI. This is not P form, P, not the one form P. Okay. This is an object which is a one form because written in the basis of DQIs, but it has component PIs. Okay. We'll see how this object arises from the variation principle. But for the timing, I just have written down an object. Okay. Now, this is a one form, obvious. From our previous notation, it is clear that this is a one form. Not only that, we can construct a two form out of this one form. Two form. We call it omega. Note that, come here, the function was a zero form. I acted D, I get a one form. So there is an operation which we call the D derivative, okay, or the exterior derivatives. The idea will be that omega acting on d theta gives you a two form. So this object is a linear differential operator. By definition, it's a differential operator. It acts on in the space of R form and gives you R plus one form. Okay. Just like there, you start with the zero form, gives you the one form. So some generalization of that. Again, in the tutorial, we'll derive its relationship, not me, Jan will derive. Okay. So you can show the rules of this will give you omega equal to, if it acts on this particular form, d pi, which this is something will come. And this is expected again, because omega is a two form, it's a wedge product which will obtain. Okay. These are indices, of course. So this, but has to be a little careful. This is the index. This is in the direction of Q, I. This is an index, I, and this is direction. Okay, clear? So this within parenthesis says these are components in the P direction. N components in the P direction. N components in the Q direction. Clear? So I will little bit hurry because I want to complete it in the first lecture. Otherwise, I'll take 2 minutes more. Okay. So you can show d omega, which is again d square theta. The answer will be 0. This is something which we will prove in the tutorial. That if you apply 2 times, the answer is always 0. D square is equivalent to 0. This is nothing but a generalization of the Cartesian test statement that dive curl is 0, right? Divergence curl is 0. Just the generalization of that statement in this more abstract space gives you this square equal to 0. If you do that, then you can clearly see that this omega, you can show that this has to be true. Because omega by definition is d theta. If you apply d again, this is d square theta. And d square identically is always 0. Okay. Good. Now, there is something else you can do with this omega. You can do what is called a directional derivative along the direction of the vector chi. Okay. And this object acting on omega, the definition, so this depends on your what kind of what should I say? What kind of lecture notes you are using or what kind of books you are using. So let me write down the definition. So let me use this notes. I think one has to be just consistent. All the definitions are correct. Yeah. So that means this object operating on dpi, which dqj, dqi, and this object you can throw, the definition will lead to that chi h vector dot dpi acting on dqi minus dpi chi h dot dqi. If you're not familiar with definition of this definition, we will do it. We'll prove it. That this is the definition coming from the fundamental definition of this directional derivatives. Okay. But for the time being, accept this as an identity And if you do that, now you clearly see this requires a component of x in direction of p's and q's, and this is nothing but pi dot dqi minus qi dot dpi. Is that part clear to everybody? Look at the definition of chi, okay? If you take the directional derivatives in the direction of pi, okay, you will give that it will give you pi dot dqi, qi dot dpi, okay? Is that clear, everybody? Okay. Now, what is remarkable is that if you use Hamiltonian equation of motion, okay, note what will happen. This guy is then del h, del qi, dqi minus plus del h, del pi, dpi. Okay. I've used Hamiltonian equation of motion. Okay. And therefore, this is nothing but dh. So if the Hamiltonian equation of motion exists, if they are true, then this directional derivative of two form omega along the direction of this vector, okay, and then is given by this equation. Okay. By the way, sorry, I think I should have mentioned that I'm choosing a very particular case for this vector, which I did mention. I should have mentioned that this is xiq is qi dot and xpi is equal to pi dot. And it's very important. What is this object then? This is nothing but the tangent vector on the flow in the Hamiltonian space. Okay. So think of a time parameter is changing and the object is moving in the phase space on a trajectory, then this vector is nothing but the tangent to the trajectory in phase space. This is sometimes called Hamiltonian flow vector. Okay. So basically in the phase space, this object is moving. Okay, of course, not in physical space, I mean phase space motion. And then the tangent at each point on the curve in the phase space, I call it a Hamiltonian flow vector. And then I have a beautiful relation, I chi omega equal to dh. And this is, in some sense, a basis of the symplectic structure. This omega has the property that this is a two form and which is d omega equal to 0. Okay. So this is a form which has this structure d theta equal to 0, sorry, d omega equal to 0 and omega equal to d theta, but also it's a two form. Not only that, along the direction of Hamiltonian vector field, it has this property that it gives by a gradient where the function is Hamiltonian itself. Okay. In that case, we called omega to be symplectic structure. I will define more generally in the next lecture. Let me just brush on here. So the whole idea of an Hamiltonian formalism is to figure it out, what is this omega from the theta? And I will convince you that theta comes from the variation of the Lagrangian. Once you know the omega, do something such that you get this structure. And then whatever is the h, you identify it as the Hamiltonian. This will be the strategy. That I give you the theta from the variation of the Lagrangian. Using the theta, you calculate omega. Then you identify the Hamiltonian vector field, some change time evolution of the system, construct this equation, and identify whatever coming is your dh. If you could be able to do it in a covariant way, this will give you the Hamiltonian of the covariant theory. Okay? The first problem would be this equation sometimes have zero mode. What I mean is that this omega will be degenerate. What does non-degenerate means? It means that if I move along any vector chi, as long as chi is not trivial, when chi is not a zero vector, this object is never non-zero. That means there is always some change in the symplectic, this omega. Okay. And then this change will be generated by H. Next class we will discuss if you have local symmetries, gauge redundancies, you may have this side to be zero. There will be zero mode of this equation. And then the construction omega becomes non-trivial. I will not discuss full detail how to take the construction, but then one has to do a special procedure via Wald and Lee, and then construct the gauge independent, I mean, in some sense, the modulo the gauge transformation, the structure of this equation, and then proceed onwards. So that will be the content of my lecture tomorrow. I'll stop here. Thank you. So I'll wait for if there is any doubt, questions. So the idea is, of course, I have not defined you how do I count. The basic idea is that you look at the points in each point, the tangent space, construct the collections of those tangent spaces. So this collections is a space, which is a huge object because this is all kind of tangent spaces are there. Okay. Add a Cartesian product of this tangent space. This is what we call a tangent bundle. So think of each point, and this tangent space is the one element of the tangent bundle. That's the way to understand. Similarly, you can define, for example, cotangent bundle. Each point you have a tangent space, which is a space of vectors. You can go to the dual, which is the space of one forms. That is your cotangent bundle. Now you can think of each point and cotangent bundle be an element of another bigger space. We will call it cotangent bundle. Yeah. So tangent bundle in some sense is cotangent bundle in some sense dual to the tangent bundle. I hope I'm not eating your time. Sorry. Yeah.
There is a mic, and if not all, most does. So just get the mic because.
Yeah, please. You're audible.
Hello? Yeah. So I guess the whole idea was to bring these all QIs and PIs into the same manifold and then do the whole procedure, because you were having a manifold where you are defining the tangent bundle of things, and in the dual that is also defined in the same manifold.
Absolutely.
So my point is, if I didn't do that, let's say I have n different vectors that construct a manifold, and other manifold is some constructed of PIs.
Okay.
Then I construct these. So if you, the way you have defined this inner product is of in the same manifold, you are defining an inner product from the tangent bundle and the cotangent bundle. So if I do that, if I take one manifold and define the tangent bundle, and out of the other manifold, I pull back the one form and then define. So would that result the same structure?
I don't know, but the idea is that you have to be careful. There are these canonical transformations. The canonical transformation, I can mix Q and P's.
Right.
Since the canonical transformations are allowed, which will leave the canonical structure invariant, therefore it is most natural to use a space where I have the symplectic vector field. Q and P's are allowed. Right. And canonical structures forms a very nice group properties which acts on these spaces, and therefore you have a very well-defined structure. Nothing of that sort will happen if you treat Q's and P's differently. But remember, you can always mix Q and P's through canonical transformations, and therefore this structure is much more useful because of the presence of canonical transform. That would be my guess.
Okay, thanks.
I don't see any further questions. Let's thank Sudipta once again. And we will come back. We'll have a coffee break now. We'll come back at 11:30 for the next course.